To understand the mechanics of classical Tamil poetry, we are going to refer to a mid-20th century manual called Yappilakka, compiled by the scholar Pallav of Kalande. This text codifies Yappilakkanam, the grammatical science of poetic composition. Unlike modern free verse, where line breaks are dictated by emotion or breath, this system operates on a precise structural logic. The rules governing ancient Tamil literature date back thousands of years. They demand absolute precision. Composing in this classical style means approaching language with the mindset of a structural engineer building a weight-bearing scaffold. This introductory page outlines the complete architectural framework that governs all traditional Tamil poetry. It is a strict 6-tier hierarchy. At the very bottom is the bedrock layer, Elithu, or individual letters. Above that is Asai, which groups those letters into metrical syllables. Those syllables then combine to form Seer, the poetic feet that establish the rhythm. The structure continues upward into lines and stanzas, but today we are only going to focus on these bottom 3 layers. These contain the core combinatorial logic of the language. By breaking down these tiers, we can see how traditional scholars transformed the 247 letters of the Tamil alphabet into a mathematical algorithm. The first step in this algorithm requires you to strip away everything you know about language. We are ignoring phonetic and semantic meaning to focus strictly on metrical duration, or mora. The system sorts the entire 247-letter Tamil alphabet into 3 distinct buckets based entirely on their temporal weight. The first bucket is quadil. These 95 letters represent short sounds. In our metric system, they carry a value of 1 single unit of duration. The second bucket is nidil. These 133 letters represent long sounds, and they carry exactly 2 units of duration. Finally, we have the third bucket, consisting of the 19 Otru and Itom characters, the dot consonants. This passage introduces a critical rule for dot consonants. They possess 0 metrical value. The author compares them to a small child on a train, physically present but requiring no ticket, so they are mathematically uncounted. By reducing the language into these 3 weights, short, long, and null, the system prepares raw speech to be plugged directly into a strict algebraic formula. Once the letters are assigned their weights, they move up to the next layer of the pyramid, asai, or metrical syllables. This top bracket illustrates the 4 formulas for the first type of syllable, a nair asai. It consists of a single short or single long letter, optionally followed by a 0-value silent consonant. Panning down to the second bracket, we find the formulas for a nirai asai. A nirai requires 2 active letters paired together. This can be 2 short letters in a row, or a short letter followed by a long one. Look at this parsing exercise. For the word va nam, va is a long letter, a nair asai. Nam is short plus silent, another nair. In the second example, pala maram, pala pairs short and long for a nirai asai. Ma-ram pairs 2 shorts plus silent for another nirai. The algorithm dictates a strict dependency. A short letter can stand on its own, but if it precedes another short or long letter, it must pair up. As demonstrated, the process of parsing a word into asai is a deterministic operation, functioning according to a strict set of letter weight rules. With our binary base of nair and nirai syllables established, the algorithm now scales to construct the third layer, seer, or poetic feet. By combining our 2 base syllables into pairs, we get a simple 2x2 matrix yielding 4 base patterns. This table connects those geometric combinations to the mnemonic words used by scholars, thema, pulima, karuvilam, and kuvilam. Each mnemonic word mirrors the rhythmic pattern it describes. The ma physically sounds out the long pattern of nair. The system then adds a third syllable, expanding the matrix into a 3-dimensional array. By systematically attaching suffixes like kai or kani, the system generates 8 and eventually 16 distinct rhythmic building blocks. This scalable matrix allowed ancient poets to calculate, memorize, and manipulate massive rhythmic grids entirely in their heads. But a rigorous system is only as useful as its constraints. To prevent the rhythm from running on indefinitely, the algorithm needs stopping conditions. We see this most clearly in the Venba, one of the most prestigious classical Tamil meters, utilized in the famous Thirukural. This table outlines a unique termination rule. A Venba poem cannot end on a standard foot. It must trigger a programmatic stop. The final word is forced to truncate into a restricted pattern, effectively locking the structure in place. The logic holds from top to bottom, from sorting 247 letters by duration, to combining them into binary syllables, to mapping them onto exponential matrices. Pulavar Kulandai's Yappilakka reveals a system of prosody governed by a rigorous, predictable framework of letter-based logic. But a rigorous system is only as useful as its constraints. To prevent the rhythm from running on indefinitely, the algorithm needs stopping conditions. We see this most clearly in the Venba, one of the most prestigious classical Tamil meters, utilized in the famous Thital chorale. This specific table outlines a unique termination rule. A Venba poem cannot end on a standard 2 or 3 syllable foot. It must trigger a programmatic stop. The final word is forced into a restricted 1-syllable or special 2-syllable pattern, effectively locking the structure. The logic holds from top to bottom, from sorting 247 letters by duration, to combining them into binary syllables, to mapping them onto exponential matrices. Pulavar Kulandai's Yappilakka reveals a system of prosody governed by a rigorous, predictable framework of letter-based logic.